Have you ever stopped to think about why you can push open a super heavy door with, like, just one hand? Or how a seesaw works, with two people of totally different sizes? Well, the answers are everywhere, hiding in plain sight. They're all about the invisible forces of physics. Today, we're going to pull back the curtain on force, torque, and motion and see what really makes our world tick. So let's start with a really simple question, one you've probably never actually asked out loud, but your body just knows the answer. Why is a door handle always way out at the edge, as far from the hinges as possible, right? Why not stick it in the middle? The answer to that simple question is going to unlock a huge concept that governs basically everything that turns or spins.
But okay, before we can even get to what makes things turn, we gotta go back to square one. We need to get a handle on the one thing that gets everything moving in the first place. And of course, we're talking about force. This is really the starting block for all of mechanics.
So in the world of physics, a force is basically any kind of push or pull that can change an object's motion. The famous formula, F equals ma, tells us something really deep. The heavier an object is, that's the mass, or the faster you want to make it speed up, that's the acceleration, the more force you're going to need. It's such a simple rule, but it explains everything from throwing a baseball to launching a rocket into space.
Now, as soon as we start talking about mass, it's super easy to get it mixed up with another word we use all the time, weight. Honestly, nailing the difference between these two is a huge step in really getting physics, so let's just clear it up right now. Okay, here's the deal. Mass is just the amount of stuff you're made of. It's a constant. It doesn't matter if you're on Earth, on the moon, or floating in space, your mass is always the same. Weight, on the other hand, is the force of gravity pulling on all that stuff. It has a direction, always down, and it totally changes depending on how strong the gravity is. So your mass is the same everywhere, but your weight, not so much. All right, so we've got a good grip on force. Let's get back to our door. When you push on a door, you're not really trying to send it flying across the room in a straight line, right? You're trying to make it rotate on its hinges. And to do that, you need a special kind of force, a turning force. And this turning force has a name. It's called torque. Torque is the measurement of how good a force is at making something spin around a pivot point. With our door, the hinges are the pivot, and the push you give with your hand creates the torque that swings it open.
And the recipe for torque is actually incredibly simple. It's just the force you apply, multiplied by how far away you are from the pivot point. This is it. This is the secret to the door handle. The farther away you are from the hinges when you push, the more torque you get for the same amount of effort. That's why it's so much easier to open a door from the handle instead of pushing right next to the hinge. Now, here's a pro tip. This is a little detail that trips up a lot of people. The distance you use in that calculation, it absolutely has to be the perpendicular distance. That means it has to be at a perfect right angle from the pivot to where you're pushing. If you get that part right, you've pretty much mastered torque. Okay, so we know how to create rotation. We know how to make things spin. But what about the opposite? How do things stay perfectly still and balanced? This brings us to this really cool idea called equilibrium. And the idea is just so simple and elegant. For something to not rotate, all the different turning forces, all the torques acting on it, have to perfectly balance each other out. They have to completely cancel, adding up to zero. This whole idea is known as the principle of moments. It's a golden rule. For an object to be perfectly balanced, the total torque trying to spin it one way, let's say anti-clockwise, has to be exactly equal to the total torque trying to spin it the other way, or clockwise. Just look at this classic seesaw. It's the perfect example. On the left side, we have a 40 Newton force that's 2 meters away from the middle. That creates an 80 Newton meter anti-clockwise moment. Now, on the right, there's a much heavier 80 Newton force, but it only needs to be 1 meter out to create the exact same 80 Newton meter clockwise moment. They're equal, and so the seesaw is perfectly balanced. It's literally playground physics. So, this whole idea of balance leads to another cool question. Is there like one single point in an object where all of its weight seems to be focused? A kind of perfect balance point?
And the answer is yes, there is. It's called the center of gravity. You can think of it as the average location of an object's weight. What's so useful is that for any physics problem, you can just pretend the object's entire weight is acting right from that one single spot. It makes the math so much simpler. For nice, regular shapes, finding the spot is pretty easy. For a square or a rectangle, it's just where the two diagonals cross. For a triangle, it's a point called the centroid. And for a circle, well, it's just the center. It's basically the geometric heart of the object.
Okay, so we've talked about what makes things turn and what keeps them still. But what about when things are already moving? In a circle. Let's dive into our last topic for today, the really fascinating and sometimes kind of weird physics of circular motion.
So here's a real brain teaser for you. Imagine a car driving around a perfectly circular track. It's holding a steady speed, say 60 miles per hour. Its speed isn't changing at all. So how on earth could it possibly be accelerating? The whole secret to this puzzle is understanding the crucial difference between speed and velocity. I know they sound like the same thing, but in physics, they're definitely not. Here's the key. Velocity includes direction. So even if the car's speed is totally constant, its direction is changing every single second as it goes around that curve. And here's the rule. Any change in velocity, doesn't matter if it's speed or direction, is by definition an acceleration. So this acceleration is caused by a real actual force called centripetal force. It's always pulling the object inward toward the center of the circle. Now, what we feel when we're in that turning car is an outward push, which everyone calls centrifugal force. But here's the twist. It isn't a real force. It's what we call a pseudo-force. It's just the feeling of our own inertia, our body wanting to keep going in a straight line. And this, right here, is probably the single most important thing to remember about circular motion. So many people think that centripetal force is the equal and opposite reaction to centripetal force, from Newton's third law. But it's not. It's just what inertia feels like in a spinning system. The only real force in this whole story is the one pulling you in.
And that kind of leaves us with a pretty deep thought, doesn't it? The physics of motion shows us that some of the forces we think we feel every day aren't actually real, not in the way we imagine. It really makes you wonder, what else that we experience in our daily lives is just a matter of perspective?